This is a recording for Elias Maela, student number 122885545. The YouTube link is on the slide. Galvanometer is a system that converts electric current into mechanical positioning system. It's made up of a needle, spiral spring, permanent magnets, and a coil to name the few. Before we dive into galvanometer design and its control system, it is important to first discuss the two fundamental types of control systems, which is open loop and closed loop system. Understanding these control system philosophies provides a foundation for analyzing how galvanometer operates. An open loop control system operates without a feedback. The system output is not measured or compared to the desired input. The controller simply sends a command to the actuator. The system responds based on the design characteristics. Consider a situation where I provide instruction without verifying if the message was correctly received or understood. Since there is no feedback obtained, this resembles operation of open-loop control systems. A closed-loop control system is a system that continuously measures its output and compares it with the desired input. Unlike open-loop system, a closed-loop system uses a feedback to determine whether the desired result has been achieved. In the case of historical galvanometer, the measured current flows through the moving coil and produces an electromagnetic torque. The coil rotates, causing the pointer to deflect. The operator observes the pointer position and interprets the current value. Since the position is not a feedback to adjust the system, the galvanometer operates as an open-loop measurement device. Galvanometer is using DC motor concept. A direct current motor is an electromagnetic device that converts electrical energy into mechanical rotation motion. Motor consists of an armature coil that rotates in a 360 degrees. When a current I in a coil with N wires, it generates force F. Using Fleming's left-hand rule, we can determine the direction of the force. Force is the product of the magnetic field, the current, and the length of the specific coil. To understand how the galvanometer works, I started by modeling it as a separately excited DC machine. The system consists of two electrical circuits, the armature circuit and the field circuit. The armature circuit carries the current that we want to measure, while the field circuit supplies the electromagnet that creates the magnetic field. To generate equations, I use Kirchhoff's voltage law. In the armature circuit of the galvanometer, the applied voltage is used in three ways. The first part of the voltage is dropped across the armature resistance. Second part of the voltage is used to overcome the armature inductance when the current changes. Finally, some of the voltage opposes the supply of the back electromagnetic force, which is generated when the coil is moving or rotates in the magnetic field. Therefore, according to Kirchhoff's law, the applied voltages must be equal to the sum of the three voltage components. VA is the input voltage, armature circuit, the equation you can see at the top, armature coil, the torque, and finally the spring load. The output of this is the angular rotation. The B on this drawing represents the damping coefficient and not the magnetic field. VF is the field voltage, and you can see the equation of the field circuit, armature coil, the torque, and as well as the spring load. Now, how electric motors convert the electric energy into mechanical energy? So the torque of the motor can be determined as the force multiplied by the B, which is the radius of the system. But we remember the F is equal to the number of turns multiplied by the magnetic field multiplied by the current that is flowing through that wire multiplied by the length of that coil. The K here represents a constant that has multiple of numbers. This can be number of turns of a coil, the effective radius, the armature geometry, winding configuration, and many more. Thus, therefore, electric torque equals to KT, KF, and IA, IF. This equation is important because it shows that the torque is dependent on both the current of the field and the armature current. Let's not forget the back electromagnetic force. As the coil rotates, it cuts through the magnetic field lines that are running from north to south. According to Faraday's law of electromagnetic induction, a voltage is induced in the coil. The back EMF increases with speed. Therefore, the faster the coil rotates, the greater the opposing voltage. This naturally limits the armature current and stabilizes the system. After establishing how the torque is generated, the next step is to model the mechanical motion of the galvanometer pointer. Applying Newton's second law, the following equation can be achieved, where Te is your electrical torque, TL is the load that is applied by the spiral spring, J is the moment of inertia, B is the damping coefficient. Unlike a DC motor, which is expected to rotate continuously, a galvanometer must stop at a position proportional to the measured current. To achieve this, a spiral spring is attached to the moving rotor. The torque of the spring is equal to K and the angle. Angular motion is now a change of angle over time. Substituting this into the equation above, we end up with the equation below. Now remembering that Te equals to Km, If, Ia, we can now equate the two. Now we have inertia, mechanical damping, the spring stiffness, and that is equals to electromagnetic torque. The response of the system to an input is not abruptly. For example, when a force is applied to the spring at the time 0 and then released suddenly later, the spring does not immediately return to the equilibrium position. Depending on the stiffness of that spring and the damping present in the system, the spring may overshoot the equilibrium position and oscillate before it eventually comes into a steady state or condition. With that, we get what we call Laplace transform. This is used to analyze system using control system technique. The differential equation is converted into Laplace domain. The Laplace domain allows us to represent the system using transfer function and block diagrams rather than differential equations that you will saw earlier on. And for open loop transfer function, we have to let Ifs equals to If0. And rearranging the equation, we get what we get when we have transfer function, which is Gs equals to output S over input S, and you can see it with this equation here. The final equation represents the open loop transfer function of a galvanometer. The input is the armature current and the output is the pointer of a needle. The numerator contains electromagnetic gain of the system. The denominator contains the dynamic behavior of the moving system, including inertia, damping, and spring stiffness. The transfer function confirms that the galvanometer behaves as a second-order electromechanical system, very similar to separately excited DC motor, except the spring limits the rotation and causes the pointer to settle at an angle rather than rotate continuously. Here is how you can improve the performance of this system. Reduce the inertia, J, by using a lighter rotor and a mirror. Increase damping, B, to reduce the overshooting of the needle. Adjust the spiral spring stiffness, K. This actually acts as a calibration method of the system because the torque is proportional to the current. Increase motor torque constant, Km. The table represents the change as well as the stability. So changing one can affect the stability, or it depends on either or. So one can always work around them. The galvanometer works by converting electrical current into electromagnetic torque. That torque overcomes the spring restraint and causes the pointer to deflect. Using a DC motor theory, I was able to derive an open loop transfer function relating to armature current to a pointer position, providing a complete control system representation of a device.